Here we have a function called Riemann, not zeta function, but Riemann raindrop function. I'll explain why it's called raindrop function. Defined as when x is equal to 0, it's defined as 1. When x is equal to a fraction, non-zero fraction of pq, of course, co-prime, q is positive, defined to be q, 1 over q, defined to be 0 when x is irrational. First of all, then we want to show the limit is 0 at any point, right, including rational and irrational. At any point, the limit is 1, 0, always 0. Now, the reason it's called the raindrop function is that this function is not even plottable. I'll explain why. You see, let's say 0, y, x. Let's say, okay, we have some maybe real number, right? Real irrational number, maybe square root of 2 or whatever. So it's defined to be 0, right? Maybe we have some other fraction, right? Fraction, maybe here we have 5 over 2, right? So defined to be 2 at the bottom, right? Half. Maybe half would be somewhere here, right? Maybe somewhere here I have 1 over 5, right? Somewhere here, 1 over 5 is here. Then it's defined to be just 1 over 5, right? Somewhere down here. But the difficulty is that we have infinitely many irrationals, right? Of course, those irrationals are all defined to be 0, right? But the difficulty is that we have infinitely many fractions, right? Each fraction has different numerator and denominator, right? Denominator could be anything, could be 2, 5, 6, 100, a million. So it could be anywhere, right? The point could be defined anywhere. Right? It could be here, there, here. So it's impossible for us to accurately plot the graph. But somehow we can maybe get some rough idea of the behavior of the graph. Right? So what we're trying to prove is that no matter at what point, right? Let's consider irrational, right? Irrational point. Maybe here square root of 2. Right? As x getting closer and closer to square root of 2, we want to show the function value is always also getting closer and closer to 0. Right? Limit is 0. So why is that? So first of all, we know that when, let me just draw another graph. So first of all, let's choose any random point, x0, right? Any real number, fix it. And we want to show that given any epsilon, right? Given any epsilon that's greater than 0, we want to show that the graph is, here's negative epsilon, but I don't need negative epsilon because the graph is already, functional value is always positive, right? Non-negative, right? Can we find a small enough neighborhood, deleted neighborhood of x0 so that the functional value can be below this line, right? Functional value could be here, there, so below this line, right? This deleted neighborhood. Can we do that? Right? First thing we know is that there's no problem with irrational numbers. Because irrational numbers, functional value is always defined to be 0. Right? So for example, in this deleted neighborhood, I can choose any random irrational. x1, right? Functional value is already 0. Right? So it's already within this epsilon, right? Within this difference epsilon. Right? So this is safe, right? x2, irrational, defined to be 0. Fine, right? Less than epsilon. This is fine. So irrational numbers are fine. The problem is rational. Right, that's where the problem is. How can we make sure that the functional value of rational numbers can be small enough? Right, how can we make sure that 1 over q can be small enough? Right, smaller than epsilon. Right, we want to show that because this is what we want to show. Rx minus 0, that's the limit value. Absolute value is less than epsilon, right? So, irrational, 0, 0, right? 0 minus 0, already 0, already small enough. The problem is that when it's not 0, when it's 1 over q, right? Don't worry about 1. Right? 1 is already defined as a single point, so the limit has nothing to do with the functional value of a single point. So this, yeah. So the question becomes 1 over q, when can 1 over q minus 0 be small enough, right? In other words, when can this happen, right? Of course, this happens when q is big enough, right? Epsilon is small enough, that means q is big enough, right? The reciprocal. So which means all I need to do is I just need to find a, for example, fix q naught. Make sure q naught is bigger than 1 over epsilon, right? The reciprocal, right? Given any epsilon, right? Epsilon greater than 0. Right, I've given any epsilon greater than 0. I can always find a q naught that's big enough, bigger than 1 over epsilon. It's always doable, right? Q naught. Now, I fix q naught. Fix q naught. Now I'm looking at this. I haven't found a delta yet, but maybe I can find a neighborhood that's x naught plus 1 and x naught minus 1, right? Not delta yet, but I will determine delta later, right? First, let's find this deleted neighborhood. So within this deleted neighborhood, I'm looking at, first of all, this type of fraction whose denominator is chosen from this set 1, 2 all the way up to q naught minus 1, right? And also the p can change, right? P can change from 1, 2, 3. So let me look at just within this deleted neighborhood, right? This not very small neighborhood, but small enough, right? X plus 1, x naught plus 1, x naught minus 1. Then I'm going to find a smaller one. Now I'm looking at this relatively bigger neighborhood. Within this bigger neighborhood, I'm looking at, like I said, p over q. Q is chosen from this finite set, 1, 2. So I'm looking at p over 1, right? P can change. P can, for example, 1 over 1, 2 over 1, 3 over 1. Can it go on forever? Can it go on forever? So which means within this neighborhood, there are infinitely many such form of fractions, right? The 1, 2, 3, 4, go on forever. The answer is no, right? The reason is because, let's say, if the top goes on to infinity, right? Eventually it's going to go out of this deleted neighborhood, right? It'll become very large. So this is obvious, right? It can only go finite. Maybe k over 1. Right? So likewise, I choose 2 from here. I can look at p over 2, right? So I can look at 1 over 2, right? 2 over 2, right? 3 over 2. Right? Or can it go on forever? Same reason, no, right? So if it can go on forever, then it'll exceed this deleted neighborhood, right? I'm just looking at this deleted neighborhood. There must be finitely many such fraction of such form, right? Can only go up to k sub 2 over 2, right? Maybe here it's k sub 1 over 1. All right, likewise, p over q naught minus 1. All right, 1 over q naught minus 1. 2 over q naught minus 1. Right? Only finitely many of them, because q naught is fixed. Right? It cannot go on forever, otherwise it'll exceed this neighborhood. Right? Maybe km over q naught minus 1. Right? So also because q naught is fixed, right? Finitely many. Right? Finitely many rows, finitely many columns, right? So in the end, finitely many number of elements, right? So essentially what I'm trying to say is that just within this neighborhood, right, this neighborhood, I have only at most finitely many of fractions of the form of p over q, where q is no larger than q naught minus 1. Right? Q naught minus 1 is fixed, right? Only finitely many choice for the denominator, right? Also for the numerator, finitely many choice. So which means, now here comes the key, which means I can easily find a smaller enough neighborhood that's smaller than this neighborhood, right? Smaller, even smaller neighborhood, so that in this smaller neighborhood, right, so that in this smaller neighborhood, I do not have fractions of such form where Q is chosen from this set, right? And P is, has finitely many options from here. There's no more such form, right? No more such element from here. So which means inside this smaller neighborhood, deleted neighborhood, the kind of fractions will all look like this. P over Q, where Q is larger than or equal to Q naught, right? Because there is no more such fractions whose denominator is from 1, 2, 3, to no more such, right? So every fraction in here must have a denominator that's at least Q naught. So what does that mean? So that means we're almost done, right? So in that case, I can easily say that Q is bigger than or equal to Q naught, which means its reciprocal is smaller than or equal to 1 over Q naught, right? Change the direction. And I said, I just found a Q naught, right? Given any epsilon positive, I just found a fixed Q naught happens to be bigger than 1 over epsilon, right? This is easily doable, which means its reciprocal is less than epsilon, right? Change the direction. So its reciprocal is less than epsilon, right? So I've really made sure that 1 over q is less than epsilon within this neighborhood, right? Which means this is exactly what I wanted. Like I said, I wanted to show that absolute value of the functional value minus 1 is less than epsilon, which means just simplify everything, which means I just need to show this, right? Get rid of 0, get rid of absolute value, 1 over q. Q is positive, right? So this is really done. Yeah, this is really true. Right? I've really found a right? So indeed, I really found a delta positive, so that when x minus x naught is bigger than 0, less than delta, right? In this deleted neighborhood, really it's small enough, right? Small enough, less than epsilon. And also, like I said, the irrationals are safe. Irrationals, functional values are 0, right? Always 0. Right? In here, every irrational number, right? Always defined to be 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Really small enough, right? Smaller than epsilon, right? Really. So, irrationals, fine. Rationals, also fine, right? Rationals, right? Both irrational rationals are both small enough, right? Smaller than in this deleted neighborhood. And we're done.